All right, so in this video, we're going to be talking about limiting reactants. Now, I know you guys have already watched a video clip and have done some practice, but I'm just going to go through and reiterate this. So if you feel like I got this, I know how to do all the calculations, you can go straight to the last problem and work that out. If you need a little bit of a refresher, then that's what this video is for. So I'm going to go through and just walk you through this using our note sheet. Okay, so hopefully some of this is a review. So unless you have a perfect mole ratio of reactants when performing an experiment, one of these things is going to get used up, okay, first. So right off the bat, we talk about reagents used up first. So we use the word reagent and reactant. Those are the exact same thing. So I know in the previous video it said limiting reagent. Now we're talking about limiting reactant. Those are the exact same thing. So something is going to get used up. One of our ingredients is going to get used up first. Okay, this ingredient is called our limiting reactant. And again, reagent is just another word for reactant. So those are our ingredients. So one of them is going to get used up first. That's called the limiting reactant. The one that is not going to get used up, where we're going to have some stuff left over, that's going to be our excess reactant. So something is going to be left over with the other ingredient. Now, the amount of limiting reactant is important because it determines how much product we actually make. So that's the important part. Okay. Now, conceptually, this is pretty straightforward how we figure this out, but mathematically, it might look a little bit weird, but this is sort of how we're going to do it. So here's our recipe. We have 1 cup. We're going to make some pancakes. So we got 1 cup of flour, 2 eggs, half a teaspoon of baking powder. That's going to make 5 pancakes. So if you want to think about this in terms of chemistry, the recipe here is our balanced equation. And you can even think of these numbers now as coefficients. So 1, 2, 1/2, and 5. Those are now our coefficients in our balanced equation or our recipe. Okay, so what we want to do is, if we look at this problem here, which says if you start with 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder, how many pancakes can you make? Now, some of you guys can do this in your head, but I'm going to show you sort of here's how we would set this up, because you can't really do the chemistry sort of analogy of this in your head. So we're going to just set this up like a dimensional analysis. And now we're given 3 different starting points or 3 different reactants. So I'm going to have to do 3 different dimensional analysis type of problems. So again, here's where I'm at. What do I want to find? I want to figure out how many pancakes I can make. That's sort of what I want to get to. So I'm going to put cups on the bottom, and I need some sort of ratio. Well, guess what? The balanced equation or the recipe is going to tell us that. It's going to say that for every 1 cup of flour, I can make 5 pancakes. So there is my mole ratio. And where did I get that? Right off the balanced equation or right off the recipe. So that means just with 3 cups of flour, I can make 15 pancakes. Okay, so visually over here with 3 cups of flour, I can make 15 pancakes. Now, I'm not taking into account the other ingredients yet. I'm just saying how much can I make with each of these. Now, 10 eggs is next. Okay, so I need to put eggs on the bottom, and I need to convert this to pancakes. So I go back to my recipe. It says that for every 2 eggs, I can make 5 pancakes. Okay, according to my balanced equation, 2 to 5. That's my ratio. So 5, so that's 50 divided by 2, so 25. So just with eggs, I can make 25 pancakes. So over here, if I just look at 10 eggs, I can make 25 pancakes. All right, now I can do the same thing with my baking powder. So In my recipe, it says a half a teaspoon, so I'm just going to use 0.5 because I don't like fractions. Half teaspoon is also going to make 5 pancakes. All right, so this is 20 divided by 0.5, so that gives us 40 pancakes. So if I just look at the amount of baking soda that I have, which is 4 teaspoons, I can make a total of 40 pancakes. Okay? Well, the question is, well, how many pancakes can I actually make with all of these ingredients? Well, I can only make 15 pancakes because I run out of flour. I can't make 25 cakes and I can't make 40 cakes because I don't have enough ingredients. So now what we're saying here is how many pancakes can you make? You can make 15. Now again, this is called our theoretical yield. In theory, according to our recipe, this is how much we can make. Okay, now a limiting reactant, that's going to come from the one that produces the smallest amount of product. So because my cups of flour produce the smallest amount of product, that is my limiting reactant. That's how we're going to figure this out. So my limiting reactant is flour. My excess reactant, eggs, and baking soda. So I have 2 reactants that are going to have some amount of reactant left over. I'm going to have some amount left over when this reaction stops. So how much of the limiting reactant is left over when at the end of the reaction? Well, 0, because we used all 3 cups. We used all the limiting reactant. It will always be 0. How much of the excess? Well, now we need to figure out, like, well, how many eggs did I actually use? So in order to make 15 pancakes, I needed to use 6 eggs. Well, I started with 10. So I can do a quick calculation here, and I can say, well, I'm going to have 4 eggs left over. Okay, I can do the same thing with my baking soda. So to make 15 cakes, I need 1.5 teaspoons. Well, I started with 4. I need to use 1.5. So I'm going to have 2.5 teaspoons of baking soda left over. So I can do that sort of just by common sense. I can come back and look at that. But mathematically, I can figure that out as well. All right, so important vocabulary here. The theoretical yield, again, this is the amount of product that should be made, okay, based on the balanced equation or based on the recipe. Balanced equation. Okay, so I can always calculate that, my theoretical yield. How much should I get according to my balanced equation? The actual yield, or sometimes it's called experimental yield, that is, well, how much did I actually make? I need to go take these ingredients and I need to make these pancakes, and I need to see how many pancakes did I actually make. We need to do the same thing in a lab. We need to figure out, well, how much of this stuff did I actually produce? So this actual number, this always has to be given in the problem unless we're going to go into the lab and do it. All right. So, let's just say I made 13 pancakes. Okay, I made 13. Well, I can compare that to the theoretical yield. According to the balanced equation, I was supposed to make 15, but I only made 13. I can calculate a percent yield pretty easily. All I'm going to do is take my actual yield, or my experimental, and I'm going to divide it by the theoretical yield, and then I'm going to multiply by 100 because I want to make it into a percent. So I can do the same thing here. I can say, hey, I actually made 13. I was supposed to make 15. What's my percent yield? 86.7. So 86.7%. That's how close I was to my actual yield, or the theoretical yield is what I should say. All right, so we can do that for anything. Okay, but that's sort of the basis for our calculations. Now, I'm just going to walk you through one, and then you guys are going to do one for homework. So it says, I'm going to start with 50 grams of aluminum and 46 grams of oxygen. What is the theoretical yield, and what is my limiting reactant? So I'm going to start by writing out the balanced equation. So the balance equation says that aluminum and oxygen are reacting with each other. And then it tells me, what is the theoretical yield of aluminum oxide? Well, I know this is a synthesis reaction. I know aluminum is +3. I know oxygen is -2. So I know the formula for this should be Al2O3. Now to balance it, I'm going to go ahead and put a 2 right here. And then I'm going to put a 3 here. That balances out my oxygens. Then I'm going to go back and put a 4. Now I have my recipe or my balanced equation. Now what's given? 50 grams of aluminum and 46.0 grams of oxygen. So I'm given both amounts of reactants. I'm trying to calculate how much product can be formed. How many grams of aluminum oxide can be formed? So that's how I want to set this up. Again, I have my balanced equation, so I'm going to go through and I'm going to do this real quick. 50.0 grams of aluminum and 46.0 grams of oxygen. Now, I see some people doing this, and this is perfectly fine. You can do it this way, where they're kind of setting it up ahead of time, and they're thinking like, well, okay, I know this is a mass problem, so I already know what the steps are going to be unit-wise, so I can just fill that in, and I can put the numbers in later. So I know this is going to be grams of aluminum. I know this is going to be grams of oxygen. I know I'm converting that to moles first. So moles of aluminum. I know moles of aluminum has to go on the bottom of the next step. This is going to be moles of O2. And I know I want to get to my product here, and I know this is going to be the mole ratio. So I know that this is going to be moles of aluminum oxide. And then the last step, I know 1 mole of aluminum oxide. I'm going to have to go back to grams here. So I'm going to use the periodic table to find the molar mass of that. So moles of Al2O3, grams of Al2O3. So I can set this up in advance. I know the middle step is the mole ratio, so I'm going to go straight to the balanced equation. 4 moles of aluminum is going to give me 2 moles of aluminum oxide. And then down here, 3 moles of oxygen from the balanced equation is going to give me 2 moles of this. I know oxygen's molar mass is 16 times 2, so this is going to be 32. I also know aluminum's molar mass is 26.98, so I'm going to put that here. And then the last molar mass, I just need to find the molar mass of 2 aluminums and 3 oxygens, and that turns out to be 101.96. So I'm going to put that here. Okay, now this comes out to be 94.5 grams of aluminum oxide. And this one comes out to be 97.7 grams of aluminum oxide. So just like we did before, we're going to look at which one produces the smaller product. And it turns out that this is the smaller of the 2 products. So this turns out to be my theoretical yield. Okay, which means the theoretical yield, or the smaller amount of product, means it came from the limiting reactant. So that means aluminum is my limiting reactant, which by process of elimination, oxygen is my excess reactant. Okay, so step 3 says the smaller of the 2 answers is the amount of product that will form and comes from the limiting reactant. I'm going to abbreviate that. So we just answered a lot of questions just by doing those 2-dimensional analysis problems. How to determine percent yield? Remember, I've got my theoretical yield, so in theory, this is how much we should make. Now, we didn't do this in a lab. They told us a student produces 38.5 grams of aluminum oxide. So this is going to be my actual yield. Again, that has to be given because we didn't do this in a lab. So if I wanted to calculate this, I'm going to take my actual yield and I'm going to divide it by my theoretical yield, which is 94.5. Wow, this was really far off. This was a pretty bad percent yield. Anything better, anything 90% or above is good. This comes out to be 40.7% yield. Not very good. Okay, but it can happen. All right, so that's all the different steps. Now, putting this all together, this should have started on the next page. It's kind of weird, but what you guys are going to do for homework is number 1 on the next page, which is kind of putting all of this together.